Section 4.1 in the Margalit textbook is a big departure from how most people talk about determinants. Most textbooks talk about determinants, and I really love it. What's unique about Margalit's approach is that he says, hey, we're going to create a function called the determinant function, and its domain is going to be all possible square matrices, and its output, or its range, is going to be a real number. All right, so I put in a square matrix, and this function will spit out a real number. And that's going to be helpful for a lot of reasons. But let's talk about the process. Let's talk about the defining properties, right? So Margalit says that this function, this determinant function, needs 4 defining properties. First of all, the first 3 are about row operations and how the row operations will affect the real number that spits out. The last one is that the determinant of the identity matrix for any square any value, any positive integer n, the determinant of an identity matrix is equal to 1. Okay. Now notice this. So a row replacement. What's he mean by a row replacement? This is where I say where I do something like replace row 2 with the sum of row 2 and 3 times row 1. Right, so that's what we mean by row replacement, where we're adding the scalar multiple of another row to that row and then replacing the original row with that linear combination. All right, now scaling, that's just multiplying through a row by a non-zero value c, and then swapping 2 rows. So notice, the swapping 2 rows will change the sign of the determinant. Scaling a row will just scale the determinant by the same value. And the row replacement doesn't change the determinant at all. Okay, so if we require a function, a determinant function, to have these properties, it turns out that this is enough. There's only one function that will do it. Okay, now the great thing about defining the properties this way is it gives us a way to go, oh, I can use row reduction to transform the matrix into some format where I can calculate its determinant. Let me encourage you at this point to please read all of chapter 4 carefully, probably a couple of times, because there's a lot of great information there. And it's hard for me to go over it, all of the great information, in a single video. But here is his recipe, what I call the key task in the section, how do I calculate a determinant using row reduction? Well, you're given some matrix, and you're going to head for REF, right? You want to do row operations and get your matrix into REF. Then we're going to talk about why this is true, but the product of the diagonal entries. I want to just multiply all the entries on the main diagonal. Remember that row swaps will change the sign, so I need to calculate R, which is the number of row swaps. And then if it's an even number, then the sign will not change. If it's an odd number, the sign of the determinant will be negative, right? And then I also do the product of the scaling factors used. Now, it turns out that this denominator is not needed. We can always reduce to REF without using scaling factors, without multiplying a row by a non-zero scalar. But in general, this is true. Okay, so what are we going to do? We're going to go to REF. We're going to remember how many row swaps we had to do while getting there. We're going to avoid this. So then I'll just calculate the product of the diagonal entries times a positive or negative 1. Before we get into an example, we need to give you some definitions. All right, so first of all, when we say the diagonal entries, what I referred to as the main diagonal entries, we're just talking about all of the entries where the row index and the column index are the same. So the a sub 1, 1 entry, the a sub 2, 2 entry, the a sub 3, 3 entry, and so forth. And this is true whether the matrix is square or not. However, the determinant is not defined for non-square matrices. All right, but it's important to know where the diagonal entries are because the next definition we're interested in is the definition of triangular. Okay, so this is an upper triangular matrix where the only non-zero entries are above the main diagonal and on the main diagonal. And we call it lower triangular when the non-zero numbers are on or below the main diagonal. And by the way, if a matrix is both upper triangular and lower triangular, then it's diagonal, right? Because triangular matrices are allowed to have non-zero entries on the main diagonal. So if it only has entries on the main diagonal, then it's both upper and lower triangular, but we have a word for that. We call it diagonal. Now, what's true about all of these and important to know is that I can calculate the determinant of any triangular matrix by simply multiplying all of its entries along the main diagonal. All right. And Margalit makes one point beyond the fact that any triangular matrix has its determinant is just the product of its diagonal entries, which I just said. He also makes this point that if any of the columns or rows is all zeros, then the determinant is zero. Why? Well, I'll end up with a zero on the main diagonal, right? If I have a row of zeros or a column of zeros, I'll end up with a zero on the main diagonal, and therefore the product of its diagonal entries will be zero. So that's one way to tell, right? These 0 rows, 0 columns in a matrix, anywhere in a matrix, whether it's row reduced or not, will let me know that, hey, the determinant is zero. That's not all of the determinants that are zero. That's not all the matrices that have determinants that are zero, but it is one way to scan for that and know about it. Finally, before we do an example, I'll just say that Margalit takes some time to prove that this real number, this determinant, always exists, and it's also unique. There exists one and only one function that satisfies the four defining properties. Okay, definitely it's worthwhile to take a look at this, but I'm not going to go through it in detail. What I will talk about is what Margalit calls the magical properties of the determinant. And this is the key one going forward, that an invertible matrix has a non-zero determinant. So I know that a matrix inverse is possible anytime the determinant is non-zero. I know that a matrix can't be inverted if the determinant is zero. So for any square matrix, we know that if the rows or columns of A are linearly dependent, right, we know that the matrix won't be invertible, and therefore the determinant of the matrix will be zero. Another magical property of the determinants is that the determinant of the product of matrices A and B is equal to the determinant of A times the determinant of B. So that's pretty cool. It's sort of like distributing, right? I can either do the product matrix first and then calculate the determinant, or calculate the two determinants and multiply them together. That property leads to two other properties, that the determinant of some matrix raised to the power n is just the determinant value, that real number raised to the nth power. And also this one, which is really, really helpful. If I know the value of the determinant of A, and by the way, this is another way that we write determinant of A. So if I use this absolute value notation and I say A equals 4, every mathematician in the world is going to understand this to mean the determinant of matrix A. And if the determinant of matrix A is 4, what does this say? It says that the determinant of the matrix A inverse is equal to 1/4. Okay, so the determinant of A inverse is the reciprocal of the determinant of A. To finish out the magical properties of the determinant, we need to talk about a transpose. All right, so the transpose of a matrix is, we call that A with a superscript T for A transpose. And we take the rows become the columns of A become the rows of A, right? So we're basically flipping this matrix across the main diagonal. And so the first row of A will become the first column of A transpose, and the second row of A will become the second column of A transpose. You'll notice that the main diagonal entries will stay fixed, right? As I do this, the third row becomes the third column. And we're going to talk about the transpose. Why? Well, because there's a couple of interesting properties. When you take abstract algebra, you'll know the shoes and socks property. But when I do the product, when I take the transpose of the product of two matrices, actually I have to reverse the order if I'm going to be able to take B transpose, A transpose. And some people call this the shoes and socks principle, that if I put my shoes on first, my socks on first, and then my shoes, and then take the transpose, right? To take them off, I have to take my shoes off first, and then my socks. Okay, so the order gets reversed when I distribute this. It's like distributing the transpose to the two matrices. The matrices have to reverse order. And those two properties that I just talked about, what the transpose is and this particular property, they're important, but here's the key. This is huge. I don't ever have to calculate the determinant of A transpose. I don't have to do the determinant. I don't have to do anything to find the determinant of A transpose. It's just the determinant of A. Okay, so that's enough about the properties. Let's actually take a look at an example. So here we are in MATLAB with a matrix, and we want to calculate its determinant. Now, just so you know, we can use the same notation basically that we're using in the book to find that the determinant of A is equal to 2. So we can use MATLAB. All right. And we can also determine some things. Here, let me just leave that. Let's see. So determinant of A, we can leave that up there. And let's do some things, right? So if we do a row swap, right, which is one thing that we're going to want to do, let's just swap rows 1 and 2. Okay. And let's not just swap rows 1 and 2, let's also take the determinant of little a. Okay. And I'm a little bit confused because this should have changed. Let's see. So the determinant of A. Let me pause this for a second. And I realized the mistake I made. The mistake with this is a capital A. So when I get everything right, there we go. You can see that the determinant of A before the row swap is positive 2. And the determinant of little a, which is A with the row swap, has a determinant of negative 2. So that was one of the first defining principles, is that row swaps will change the sign of the determinant. All right, so let's proceed on. I switched the rows just so it will make it easier to get a, I'll get to work with whole numbers a little bit longer if I have a 1 as my pivot instead of a 4. So let me jump in here and do the next thing which we want, which is to take row 2 times minus 4 times row 1. So we're going to have row 2 equals row 2 minus 4 times row 1. All right, and notice that that didn't change the determinant of little a, right? So doing one of these row replacements doesn't change the value of the determinant at all. And now notice what we have. We have a triangular matrix, so to get its determinant, I can multiply all the values on the main diagonal. So let me jump out of here and calculate, right? So our value D for the determinant will be 1 times the negative 1 times 2, right? I'm just doing the value of the main diagonal entries, the product of the main diagonal entries. Then I take minus 1 raised to the number of row swaps. Well, we did one row swap, all right? So when I calculate when I calculate the determinant, notice that I get 2. And if I calculate the determinant of capital A, I get 2, right? So just, that's the key, that I can row reduce, take the product of the main diagonal entries, and then figure out the sign by remembering how many row swaps I had to do. Here I had to do 1. If I do an even number of row swaps, it won't change the sign. This term will be a positive 1. And if I have an odd number of row swaps, then this term will be a negative 1. Okay? So that's the process for finding a determinant. And that's pretty much the key task from this section. You should definitely read it. The explanations and examples in the textbook are great. And this is how we're going to both define and understand how it is that we calculate this determinant right here. Right. We're going to reduce to REF. Once we reduce to REF, we'll take the product of the main diagonals, and we will adjust the sign by the number of row swaps. Final thing, it should be clear, but maybe I haven't made it clear. I don't need to multiply any row by a non-zero scalar to get to REF. Now I do need that to get to RREF. Remember, in REF form, my pivots can be something other than 1. They can be -1, they can be 6, they can be 2. In this case, we had 1 and -1 and 2 were our pivots, right? But since we don't need the pivots to be 1, we don't ever have to multiply a row by a scalar to get to REF. The only thing that I'll have to do is sometimes I'll have to do a row swap because there's a 0 where I need to put a pivot. And sometimes row swaps are going to be my only option to convert to REF. However, other than row swaps and row replacements, I don't need that third row operation to get to REF. And once I'm in REF, I will have an upper triangular matrix, right? That's kind of the key trick. Not all upper triangular matrices, well, excuse me, all matrices that have been reduced to REF are upper triangular matrices, right? So REF form always implies upper triangular, and we know how to calculate the determinants of upper triangular matrices. So that's the process. Again, definitely go through the I've made some textbook notes, so you can go in and check that out. And definitely read the Margalit text very carefully, all of chapter 4, and plan on rereading section 1 a couple times.